So we know that the modeling process is 3 steps. We have to choose a model, choose a loss function, and then minimize average loss in order to determine our model's optimal parameters. Well, we have our model expressed in matrix vector notation. Let's take a look at the loss. So in this video, I'm going to start off by looking at 2 seemingly unrelated ideas, and then at the end, I will sort of combine them and hopefully things will start to click. Let's start off by talking about vector norms. The norm of a vector is some measure of its size. Now, there are more formal definitions of vector norms that you may have seen in your linear algebra course, but we don't really need them for our purposes. There are 2 vector norms that we will sort of study in Data 100, and they're called the L1 and L2 vector norms, and so these names should sound familiar to you. L2 will be the norm that we use today, but the L1 norm will appear in a few lectures from now. But let's take a look at the definitions of both. So let's suppose our vector x has n elements, x1, x2, x3, so on and so forth, through xn. We define the L2 vector norm as being the square root of the squares of the elements in x. So it's the square root of x1 squared plus x2 squared, and so on and so forth, through xn squared. The L1 vector norm is the sum of the absolute values of the elements in x. So the L1 vector norm, which we denote with this subscript 1, the L2 norm has this subscript 2 here, we say is the absolute value of x1 plus the absolute value of x2, so on and so forth, through the absolute value of xn. Let's talk a bit more about the L2 vector norm, since it will be our primary focus in this lecture. The L2 vector norm you can think of as being a generalization of the Pythagorean theorem into n dimensions, and you can interpret it as being the length of a vector. We say that the distance between 2 vectors is the L2 norm of their difference. So for instance, if A and B are 2 vectors of the same length, their distance is the L2 norm of the vector A minus B. And this is something that we will heavily use in this lecture. Lastly, if you look at the square of the L2 norm, it's equal to the sum of the squares of the elements in X. So if we look at the square of the L2 norm, which is what this notation is saying, we have the L2 norm and squaring it. So these 2 2's mean different things. It's just equal to the square of the elements in X. x1 squared plus x2 squared, and so on and so forth. So the square of the L2 norm of a vector is the sum of squares of the elements in X. So that's vector norms. Now let's pivot and talk about this idea of a residual. Now, a residual is defined as being the difference between an actual and predicted value in the regression context, which is what we're looking at right now. For several reasons, we use the letter E to denote residuals. In some cases, you might see the letter R being used for residuals, but we use R for the correlation coefficient, so let's stick to using E for now. We denote the ith residual E subscript I as being the true y value for observation I, so yi, minus the predicted y value for observation I, so yi hat. So this is the definition of the ith residual. And physically speaking, the residuals are the distance between our true point and their prediction on the line. So for instance, the third residual E3 in this scatter plot would be the distance from the true y value for observation 3, which is up here, and the predicted y value for observation 3, which is down here. So in this case, the residual is positive. In this case, the residual is negative. You can think of it as being sort of what's left over after we make our prediction. Now, the term residual might be slightly new, but the idea of a residual is not. The mean squared error that we've been looking at is the sum of the squares of the residuals of our model multiplied by 1 over n, right? yi minus yi hat is just the term that we've been squaring and taking the mean of all along. So this is really nothing new. You may see where we're going with this. We can actually stack together all of our residuals into a single vector, which we call the residual vector E. So our residual vector is this vector of the first residual, the second residual, so on and so forth, through the nth residual. So this you could think of as being E1, E2, so on and so forth, through En. Now this residual vector is just the difference between our vector containing our true y's and our vector containing our predicted y's. So So this is the true response vector, and this is the predicted response vector. And we say that that is the residual vector. And so putting all of this together, we know that our loss function, once again, is going to be squared loss. And so the average loss across our data set is mean squared error, which we can write as being 1 over n times the sum of residuals squared. In our case, our model for a single observation yi hat is the dot product of the ith row of our design matrix with our parameter vector theta. So this is what our average loss looks like in terms of individual observations on their own. But from a previous slide, we established that the square of the L2 norm of a vector is the sum of the squares of its elements. So here we are summing the residuals squared, and so we can just replace this term, which is, the same as this term, with the square of the L2 norm of the residual vector. And so that's precisely what we've done down here. Substituting in our model y hat is equal to x times theta brings us to this expression, right? And this, again, is an equivalent way of writing our residual vector. And so this right here is our average squared loss across our entire data set, and we are looking for the value of theta that makes this quantity as small as possible, that minimizes this quantity. Now, before we proceed, I wanted to note that we will employ a similar trick to what we did in the last lecture. The value of theta that minimizes 1 over n times the square of this vector norm is the same value of theta that minimizes just the square of this vector norm. Having the 1 over n out front doesn't change the value of theta that minimizes this quantity. So our goal is really to find the value of theta that minimizes the squared L2 norm of the residual vector. But since the residual vector is just the difference between our true y vector and our predicted y vector, what we are really trying to do is minimize the distance between our y vector and our y hat vector. Now, there are two ways that we can go about doing this. One way is we could use calculus, as we've done earlier, and in fact, earlier iterations of Data 100 actually used to do this in class. However, it is pretty linear algebra heavy, and so for now it's out of scope. But I've provided a link in the slides if you're really interested and want to take a look at how this proof might work. The simpler way to go about doing this is by using a geometric argument, and that's what we're going to do here. And in this argument, the sort of motivating idea is that we want to minimize the distance between our true y vector and our predicted y vector. So let's do it.